matrix.
So because I'm maybe too naive, how about your gauge is local gauge or global gauge? I don't know.
By gauge, I always mean local.
Okay, so you're using local. Thank you.
So if you look at this, say, paths with a lot of internal legs, there are a huge number of gauge redundancies. Okay. So then, what do I mean by a symmetric wave function? So what I mean is, I start from a path, for example. I apply some gauge apply some physical symmetry transformation. G is in the symmetry group. Then the tensor will generally transform to some other tensor. So this symmetry can be either the internal symmetry like spin rotation, or some spatial symmetry like translator symmetry. For example, this guy can move to there. But then what I require is after the symmetry transformation, I can send the wave function back by a gauge transformation. So after I apply the G together with this WG on the virtual leg, the tensor network completely go back to itself. That's the assumption. So this machinery that I was talking about is about how do I systematically classify this kind of transformation rules. So the global symmetry transformation become implemented on the virtual leg as some gauge transformation. And I have to find a way to classify this inequivalent WG, basically. So that's the goal. And the question is, what's the consistent conditions for this WG? The WG cannot be arbitrary, so I have to satisfy some consistent condition. So let me just use the remaining maybe more than 10 minutes to talk about something very simple. I think about one dimension. And this was worked out before. So think about one dimension. So here, this if you plug in d equal 1, this is like H2 SG equal 1. So this is related to the project representation with the second cohomology group. So the famous example is this AKLT chain, which was mentioned earlier. But the claim is this SG can be, if you think about like a complete classification, this SG can be taken as the full symmetry group, including everything. And in particular, this mirror symmetry in this SG will be treated as anti-unitary. So maybe the main purpose here is to demonstrate, this is somewhat surprising, that this mirror symmetry should be treated as anti-unitary in this classification. So think about MPS, very simple. So I want it to be symmetric. So then I know this tensor will have to be equal to this G transform tensor together with the WG. So then the question is, what's the consistent condition this WG has to satisfy? So you can ask yourself, I have two group element, symmetry group element, G1 and G2. So I can apply this G1, G2 in the following way. I apply G2 first, and then G1 later, or I apply them together. The question is, are they the same? If you think about it, you tend to think they are the same, because as I mentioned, so this GWG combined together send the tensor network completely back to itself. So both sides will send the tensor network back completely to itself. And both sides include the same physical transformation. So the way they transform the physical degree freedom are identical. So you may think they are the same.
So what is G1 and G2?
G1, G2 are two symmetry elements. Like say think about G1 as a translation, G2.
On the same side.
No. So here when I write this, maybe okay. So sorry, I should have mentioned this. So you should visualize this WG and G as the transformation on the whole tensor network. So this will define the transformation on the whole tensor network. Okay. So, the point is they don't have to be the same, and so they both send the tensor network back to the same tensor network, and they are the same on the physical degree freedom. So if they are different, they at most they are different on the virtual degree freedom. Okay. So then you should ask yourself, are there virtual transformation on the virtual lag only, completely virtual transformation? And they said, so because all the W's are gauge transformation. So this, you should ask yourself, are there virtual gauge transformation that leave all the tensor completely invariant? And then there are the following possibilities. You can multiply some phase chi and some phase chi inverse in this way. And so obviously every tensor will come back to itself. So such gauge transformation, this is gauge transformation. It's very special. It's a subgroup of all the gauge transformations. So we call it the invariant gauge group. So what's special about it is usually a gauge transformation will change the form of this local tensor. But this guy even leave the local tensor form invariant, completely invariant. So, but both sides have, at the most, they can differ by this IgG element. And this IgG is a single U1 phase over the whole lattice. Here I'm thinking about infinite lattice for simplicity. Just one phase, one U1 phase. So you probably can see where this U1 phase comes from. So then you realize these two guys don't have to be the same, they can differ by this phase. This phase is a function of G1, G2. Okay, so this is like this. Then you can check the associativity. So this chi G1, G2, what you can do is you say you have three transformations. Then you can move them together in different ways. You can group this group first, then this with that later, or the other way around. So this associativity gives you some consistent condition for the chi. Which is this. So here there's a group action. So the more precisely, this group action is it's like a G1 chi G1 inverse. So this is defined to be the group action. So this is just a notation. Okay. So here the highlight is if your G1 is say time reversal symmetric, then this will send the chi to chi inverse, which is a conjugate. But even for mirror symmetry, you realize no matter you put the mirror here or there, you always send the chi to chi inverse. So mirror symmetry also like anti-unitary. So that's the highlight. So this is obvious in this formulation. So chi has to satisfy this consistent condition. But then you can ask yourself, can we tune this away? Can we somehow do some gauge transformation or do some trick to make this chi to be identity? So for example, there's a WG1, so for the group element G1, there's a WG1. But it's perfectly fine to redefine the WG1 by multiplying it with a chi. And that's certainly serve equally well as WG1. So the WG1 has this ambiguity. So similarly for other WGs, they also have ambiguity. So if you tune this ambiguity, this chi will transform in this way. And again, there's a G1 group action. So mathematically, this is exactly about the second group homology. So to classify the inequivalent class of this chi, what you really try to do is to find those chi's that satisfy equation 1, and you can deform this chi up to equation 2. So the equivalent class of these group functions are exactly this H2. So here, the point is obvious. So if you do translation, the chi will do chi, but if you do mirror, chi to chi inverse. So in this formulation, it's obvious how this is. So this is exactly the algebraic structure of group cohomology. So the symmetric group can be taken as a full symmetric group. So this is a one-dimensional case. So maybe since I don't have too much time, so let me. So I will go to dimension 2 next time. But maybe let me give you some very simple example. So let's think about this dimension 1, right? So I use the remaining a few minutes just to give you some very simple example. So think about my symmetric group is identity and time reversal. Okay. I only have time reversal. So on the physical leg, I have a Kramer singlet, time reversal square equal +1. So I want this wave function to be time reversal symmetric. So I will require the time reversal acting on the physical states together with the W will send the tensor back to yourself. Okay. So then it turned out that this relation simply means our chi time reversal, and the chi identity time reversal equals chi time reversal. This chi time reversal means so this chi time reversal, which is nothing but W time reversal times W time reversal conjugate. So because you basically apply time reversal twice. When you apply once, you take a W. When you apply a second time, this will be conjugated, and then you multiply W again. So this will give you this chi. So times time reversal identity. So you can easily convince yourself that you can take a convention such that this is just identity. Because this is related to the relation involving identity. So if I have an identity, either G1 or G2 identity, I can choose this chi to be identity. So here I have time reversal action. Okay. So what this tells you is this product will be a phase. There's a time reversal action on this chi. So which just means I will take the conjugate. So chi needs to be chi conjugate. So chi can only be ±1. And this the exactly corresponding to on the virtual leg, you have a Kramer singlet only, or on the virtual leg have a Kramer doublet only. So they correspond to this ±1. So it's like Kramer square equal +1 or -1. So the AKLT chain corresponding to time reversal square equal -1. And similarly, you can use this to construct, say, for the mirror symmetry square will satisfy exactly the same algebra. So the mirror symmetry square can be +1 or -1. But for the mirror symmetry, it turned out you have to work out for the mirror, because mirror symmetry will send this flip these two legs. This is slightly more slightly different. So it turned out that for the mirror symmetry, it's a P. So P is a mirror. It turned out that so the similar relation will be about this guy equal chi, and it will be +1 -1. So this corresponding to this transformation is symmetric matrix or antisymmetric matrix. And so they're like measurable signatures of this in entanglement entropy, entanglement spectrum, which I probably don't want to mention, so I will stop here.
example that I've seen are Zato symmetry, like time reversal or parity. So can we generalize the argument?
Yeah, say it again.
Usually what I've seen are Zato symmetry, like time reversal or parity. Can we have more general?
Oh, of course. So, yeah, so you can, for any symmetrical group, you can, okay, and for any discrete symmetrical group, this H2 is sort of well defined. For continuous symmetrical group, so we'll have to take some definition, some physical definition. So you can compute this, and for every one class of it, so you compute it, you will generate, for example, it turns out that H2 of D2 conversal, so this equals D2. It means there is two classes. If you replace this by some other symmetric group, you will get something more. And for every one of this class, you can construct this chi. And for this chi, you can construct this W. And with this W, you can construct the tensor network. If you know the W, you know how the tensor transform. And then you know this. So basically, this tells you that this tensor will live in a local subhyper space. If I don't have this transformation rule, the tensor can be any arbitrary state in that Hyper space. But if I know this W, so this has to be live in a subhyper space. And then this subhyper space will give you a generic construction for this.
So is this construction restricted to SVD based, or can we?
So I'm talking about 1D. So one-dimensional case, the only trivial state is SVD, but I will do it for high-dimensional data.
So in high dimension, we can also use this to SET based.
Yeah.
Okay.
SET, SPT.
Just to see how cohomology degree is P plus 1, how to see that?
P plus 1. Yeah, so, okay, so of course in this example is clear, but so in our framework, in fact, we didn't assume we know this cohomology. It's like, so here is like an example in 2D. So you don't have to assume you know cohomology. All you have to assume is your tensor network has this IGT.
I'm asking why just D plus 1? I'm asking a trivial question. What the degree is D plus?
It's just a come out. Just come out from the
Maybe there should be some intuitive understanding.
Okay, so I can give you some other intuitive understanding, but not based on tensor. So roughly speaking, this HD plus 1 is about the topological invariance in the space-time. So that's basically related to the some partition function in space-time. Like a T graph. So this HD plus 1 is really about the.
To me, it's a really similar to number 1, some kind of cycle condition. So I want to see why we need a D plus 1 argument for the group element to state the consistency or associativity law in this experiment.
This associativity will always look like this. But somehow in higher dimension, the cohomology is not directly come from this associativity. It's going from, you have to do some further steps. So I will explain that.
Any more questions? If not, let's thank Ying and all our speakers.